This podcast is about regression analysis, first about the univariate case. This podcast corresponds to Handouts Chapter 12. We will be dealing with some theory and model for the univariate regression case, and then we will see how we do univariate regression using R. A next podcast will be devoted to theory and model of multivariate regression and the corresponding part in R. Let's start with theory and model for univariate regression. The general idea of regression is that you have a set of points given, a point cloud in the xy plane, and you would like to find the best fitting line to these points. Of course, this line will not really be connecting, but it will be lying such that some kind of distance to the points is minimal. As we have learned, or as you may remember, the minimal distance is the squared distance parallel to the y-axis for each point. We sum up all these squares, and this thing needs to be minimal. We see this again in the illustration down here as mathematical statement that we choose this minimized squared error. There are also other options of choosing a regression line, however we will not be dealing with that in this course. Of course, drawing a regression line by hand is always something difficult. Usually you cannot really tell whether the red line here or the green line would be appropriate for the corresponding data. Now, what are the model assumptions that are behind a regression analysis? The first and very important assumption is that you have two kinds of data, an independent variable x and a correspondingly dependent variable y. That means that for each x independently chosen, for example 3, you have a measured value of y, here for example 2.1, or for a value of x equal to 3.2, you have measured a value of y of, let's say, 1.9. Dependent and independent. Y is a function of x. In terms of a mathematical model, we write our data points yi and xi in a so-called linear relation. That means we have yi equal to a times xi plus b, and now we have seen that a line will not perfectly connect all the points, meaning that we will have some errors, and this is the epsilon I. Epsilon I corresponds to these values here. Now there is an assumption on these errors, namely that they are normally distributed. Especially consider that the parameter sigma, which is the standard deviation, is constant over all the points yi, xi. The main questions you should be asking when you're dealing with regression analysis is the first one: does the line fit the data? Is this regression line something reasonable? You can investigate it by eye. Are there any outliers distorting the results or the regression line? Outliers can lead to the fact that the actually approximated data, approximated through the red line, is distorted, and the regression line becomes the green line due to the outlier lying very far away. So the outlier should be possibly removed. Then the next question: do the residuals meet the assumption of normally distributed? We will see how we check that. Then we would like to know whether the calculated parameters slope A and offset B are statistically significantly different from 0. In other words, the black points, they are clearly lying and forming the black line. But does the green point cloud really yield a linear model? Is it reasonable to assume that the green points are linearly distributed? And that will be assessed by looking at the significance of the slope parameter and of the offset parameter. Mathematically, we will be able to do t-testing for these parameters, but we will not go into details here. And then question number 5, is the overall model significant? This relates to question number 4. If the parameter slope and offset are significant, then the whole model will be significant. The significance of a model can be assessed by judging how much variance lies in the residual and how much variance lies within the data. If you remember statistics well, then you would remember that testing the ratio of variances is done with a so-called f-test. And indeed, the significance of a regression model will be calculated through an f-test. So intuitively, this means that in the case here, with the green data, we do not really remove variance from the data by taking into account the green line, because the residuals for the green line, they are very large and having correspondingly a very large variance. In contrary, the black line there, we have very small residuals. So indeed, it is worth doing the line because the overall variance in the data is much higher than the variance in the residuals, leading to a significant difference in variances doing an f-test. Now let's address these questions all a little more precisely. The first question, does a linear line fit the data? Well, here we have two examples where it clearly does not. The example on the left is a piecewise linear function where we would have to split the domain of interest into the left and the right part. And on the right side we have a clearly non-linear model or non-linear behavior. The questions 2 to 5 from the last slide, please scroll back if you don't remember, will be addressed soon. Before we address those questions, let us see how we can perform a regression analysis using R. It is not too difficult, as you may have expected. We start with entering some data. You could also do this with reading in a file. And then the command for doing this regression is called ln for linear model. We would like to explain the variable y in terms of the independent variable x. That's why we write y tilde x, y explained as a function of x. We name this result, or we store it in a variable, which we can then display. What we see is the parameters of our regression line. The intercept is the slope, is the offset, the y-Achsenabschnitt, and the value of the coefficient is the value of the slope, Steigung, or mathematically speaking, we have a function y of x equal to 0.89 times x plus 0.39. This corresponds to the red line we see here. This line can be plotted by saying plot xy. Now please note that the order of x and y is reversed to what it was in the linear model. To draw the regression line, we can say AB line of the regression object, maybe in color red and a bit fat. This is a good type of visualization because you visualize the point cloud and the regression line as well. Now, so far, this may be already known. Now, how do we do statistics on this regression line? So how do we assess whether our model is significant? And this can be done with the command summary of this regression object. Let's have a closer look at this. So the command summary yields, first of all, information on the residuals. We can neglect that at this point and just inspect the residuals optically later on. Then what is very important is estimates of the coefficients. So you see the intercept estimate and the slope estimate. What you also see is an estimate of the standard error of the intercept and of the standard error of the slope. So of course this slope parameter as well as the intercept b, they are subject to noise, to statistical noise. Right, so you make measurement errors and everything, so these parameters are estimated from data, which is why they cannot be precise. They are estimates. The next thing you see is the t-value. As I said before, that to assess the significance of these coefficients one can do something with a t-test, no details here, but what's very, very important is there the last column, the probability that this value is larger than the tabulated t-value, or in other words, the p-value giving the significance of the coefficient. So in this case here we see that the intercept is not significant, it is 56%. However, the slope of the line is significant, it is 0.0026, which is 0.26%, which is highly significant. The stars that you see here are an abbreviation for so-called significance codes. We are usually using the dot for 0.05. Then you have some more information here. You have information on the residual standard error, on the degrees of freedom you neglected. What is important, however, is the so-called multiple R squared. This is measuring the quality of the regression model. So if your regression model is of very high quality, then you will have a very high R squared. R squared usually is between 0 and 1. Here we have a very low R squared, meaning that our model is not qualitatively extremely valuable, or in other words, as you may remember, the correlation between the two variables that we have checked, the correlation between y and x, is not really high. Nevertheless, you have a significant slope or significant correlation, which however is just not too high. Again, here you see the p-value of the whole model, which corresponds to some kind of ratio between variances of the whole data and the variance that you reduce within the model. So there are several definitions of this f-test to be performed, so we will not go into details, just that you have an intuition. This gives you a ratio of variances for the full model and the regression model. And of course, the more variance is explained by your regression model, the better your model is. Now, we are not really satisfied with what R does by default. That's why there is a library from IAS, which we programmed to visualize some important quantities in regression. This library is tests and visuals.r. It contains many more things, for example, also the analysis of variance, clustering with the letters. So feel free to play with this toolbox. For regression, we have a function visualize regression, x, y, and you can give a p-value. Observe the source command. You need to have that file tests and visuals into the folder in which you are working or in which R is set, and then you can just load all the available libraries or all the available functions in there with the command source. And one of these particular functions is the function visualize regression. So what does this function yield? You need to provide it with the independent variable x, the dependent variable y, and a confidence value here, capital P. What you get is the following. First of all, you see the points plotted. That's very clear. then in red you see the regression line. But you do not only see the regression line, you also see a confidence band of the regression line. You know about confidence band. You have seen confidence bands of mean values, for example. So now we have a confidence band for a whole line. So we can say that with probability capital P, the regression line lies within the violet trumpet curves. These curves are really called trumpet curves due to their very characteristic shape. The p-value can be adjusted, it can also be changed here. As I said, it is 0.95. It is important that you understand what this p-value means. So this means that if you have actually a full population, then the true regression line for the full population would really lie within these bands with 95% chance. Now there is another important band pictured here. It's the prognosis band. Now this is something slightly different. If you have the challenge of having an x value given, let's say 2.5 is given, and you ask yourself, what y value will I observe? And then you intuitively just go up to the regression line and say, well, the y value I will observe is around 8. However, there is statistical noise involved, right? So the points do not lie on this regression line. You have a certain spread around that line, and in order to capture that spread, you have the prognosis interval. So that tells you that the value for y at x equal to 2.5 is in between this band with again the same p-value 0.95. So this is the prognosis band. The expectation value is still 8, of course, right? Because that's the value on the line. But if you want to have a confidence interval, then you use the prognosis band to derive that one. Now you see more things on this plot. You also see the value of the slope and the value of the intercept with corresponding p-values. So in this model, observe that the slope is not really significant. This can also be seen in quite large prognosis intervals, or in quite a large prognosis band. It's not at all clear that your value is even close to what the regression line is telling you. On the right side, you see an analysis of the assumptions used. So we have said that you should have a closer look at the residuals, because the residuals should be normally distributed. Meaning, you should see a normal distribution. Now a normal distribution is not so obvious when you just see points. That's why we have several means of help. The first two means are up here. It's two tests for normality. Please remember, the null hypothesis of these tests is saying that the residuals are normally distributed. So you want to have a high p-value. So in this case we would have normally distributed residuals. There is a second mean of assessing normality, and this is the QQ plot. We will not go into details with this plot. It just is a way of comparing a distribution from samples, which are your residuals, to a theoretical distribution, which is your normal distribution. And if your data is indeed normally distributed, then you would expect the points to lie very close to a line here. Now, of course, this is not a very strict criterion. We cannot always perfectly tell whether data is normally distributed. There is one more thing you should observe in this picture. You should observe that there is no structure within the residuals. meaning that they are homoscedastic, having always the same variance. So something like this would be very bad. The model may be significant, everything may look fine, even normality may be okay, but there is a structure within the residuals, meaning that actually your model is not okay. Now just a short repetition of all what we have said. So in this output we see the coefficients and their significance. Of course, the smaller the p-value here, the more significant the effect. Null hypothesis is always that we have a model without the respective coefficients. The confidence band for the regression line, also called trumpet curve. This provides the error interval for the regression line on a certain confidence level, capital P, which we have chosen to be 0.95 here. Then we have the prognosis band. This is a y value for a given x value, or in other words, it is a confidence interval for a y value on a given x value. And again, you can choose the confidence level of this confidence interval. Here we have 0.95, so with 95% chance the value belonging to some certain x value is within the green interval. The residual plot, again summarizing, we see the distribution of standardized residuals. This is a small remark we just make here. Standardized means that we scale the residuals by their variance, allowing us to assess them more precisely, mathematically speaking. We can assess whether the residuals are equally distributed around zero, whether they depend on the fitted value provided by the regression line, meaning that they may make something like this, and if they are homoscedastic, meaning that the variance is always around the same and not something like this. Then there are other means of assessing normality. So the two tests we have discussed with the null hypothesis of normal distribution, where you want a high p-value, meaning that your data is actually compatible with the normal assumption. The QQ plot, quantile plot, no details here. If the values lie more or less on a line, then you are fine with normality. Now let's finish this with looking at some examples of cases you will very often meet in practice. We first look at the effect of different variances in a model. We look at nonlinear relations, at outliers, heteroscedasticity, and so-called pseudometrical values resulting from some questionnaire data here, for example, data between 1 to 5, which is not really metrical. The regular case in regression, we have small variance, very clear picture, there is not much to discuss here, and so the model is very obviously telling us that we have a very good regression line, very high significance for the coefficients, very tight confidence and prognosis bands. The normality is fine here from the tests. From the QQ plot, this may be a little unclear, but this is difficult to tell. There is no structure in the residual plot. If we do increase our variance, it now optically looks a little more delicate, but still the model is giving us very good results. Especially we still have very highly significant model parameters, but we observe that the corresponding bands are getting a little more widely spread. If we have huge variance like here, one must clearly say that optically you would not be able to draw a clear and good regression line. And so the statistics get also a little more delicate. We see that still the model or the coefficient slope is still significant, but the intercept is not, because the p-value is larger than 0.05. Correspondingly, we see larger prognosis and confidence bands. The normality is not necessarily a problem, we just have higher variance. So this is something that may be worth a remark. It may not be expected that such a large variance can be handled by such a model, but regression will never fail due to large variances as long as you have normal distribution. So mathematically, regression is a very valid model in here. Practically, it may be very questionable. Then we have another case, non-linear relation, very clear here. So a regression model will capture some of it, but it will definitely not understand the full structure. Anyway, it is possible that your slope as well as intercept are highly significant, as in this case. Your normality assumptions, at least for Kolmogorov-Smirnov test, are met. The Shapiro-Wilk test realizes that there is something going on. QQ plot is also a little weird, but what's the most clear indicator for such a nonlinearity is the residual plot, where you see that you have a very clear structure. So here you have to be very careful. Of course, your model is significant because you reduce an extreme amount of variance that you have within your data. So the variance that you have after your regression is much slower than the variance you have just inside your data. So mathematically speaking, regression is not unfeasible, but the model is just not what the data looks like. So in this case, you will not want to model your data with a straight line. So what can you do in this case? Well, the easiest thing, if so very complicated to do in terms of choices, is a transformation. There are two very typical transformations, the log transform and the square root transform, just meaning that you take the logarithm of your y values or the square root of your y values. If these two transforms fail, then, well, good luck. It's always a bit tough to find good transformations that fit nonlinearity. It can also happen that residuals that you had before may not be normally distributed afterwards, so please be careful and always have a clear look at the residual plots, especially if you have applied some transformations. So in our case, if we transform the data we just have seen before, first of all observe that we get some warning here, because some of the data may be negative and the logarithm or square root of negative data is not available. So be careful about that. But we see that now we more or less fit with a straight line, despite the fact that we will have a very clearly heteroscedastic picture. So this is actually what happens if we apply the regression analysis. We see that the model is highly significant. It optically looks fine, at least concerning the red line, but we see that the confidence bands may not really measure the confidence at all the places. So here we would have probably something like this, because the confidence is much higher in this region than in the other one. But the linear regression model doesn't capture this behavior. So what you will see in the QQ plot here, that you have actually not normally distributed data. You see that from the tests, you see that from the QQ plot, and you see this in the standardized residual plot, where you see that you clearly have heteroscedasticity. So in this case, you should interpret the model very carefully. What can go extremely wrong is the prognosis band. It can be completely wrongly set. Then another very important issue is outliers. Outliers are points that are just measurement errors, usually obvious ones, in bad cases less obvious ones. These outliers have a very strong effect on a regression line because we are taking squared errors in order to optimize our line. So what actually counts is not just the distance to the line, but its square. So such an outlier will have a very, very strong influence on the regression line, and that's why it's important to take it out of the picture. Now you see such outliers also in the residual plots or in the QQ plot. Maybe they are already sufficient to destroy the normality assumptions. So please eliminate. Here is an even more clear case. This is a really bad one. Here you see that the regression line, which should actually be the green line, turns into the red line just because we have this outlier which clearly has to be removed. This outlier is almost sufficient to kill all normality assumption, at least for Shapiro-Wilk, not for Kolmogorov-Smirnov. It is very clear that you have done something wrong from the residual plot. There is still a clear structure, and also in the QQ plot you see that there is something going wrong. The effect of such an outlier at the very end of your data is huge. It's a huge leverage effect onto your regression line, meaning that you may have highly significant coefficients despite of an absolutely not fitting model. This is very difficult to recognize without having a visualization at hand. This is why this package is so useful. Now you can always argue about outliers that it's delicate to just remove data. That people are often scared to delete some data. But you should really consider that using messy data is similarly problematic. Please keep in mind that if a visualization of the calculated regression line may not be possible, which you will see in the multivariate model case later, then you have to consult the residual plot, and there you can hope to see outliers. Now some more examples. One example on heteroskedasticity. This is a very clear picture, right? The variance in your data just is increasing. This shows usually quite clearly in the residual plot. In the normality assumptions and in the QQ plot, but also directly in the regression plot. But the problem is now how to handle this. This is not so clear. There are some variance transforms, but this is highly advanced stuff and is usually very specific to certain examples. Then the last example is about pseudometrical data. This can be questionnaire data. You see here that you may have a scale from 1 to 14 or 15 where people can give answers, and this leads to such patterns. This is not really metric because in between there is values missing, but still you would feel rather comfortable drawing a regression line through this data, maybe along the green line. Maybe you should also do that. If you do it actually, then you will observe that the model can be highly significant. It also looks rather okay. It looks definitely homoskedastic. There is no structure in the residuals, and even the QQ plot looks more or less okay, and also the tests for normality seem to be fine here. So optically it's very easy to identify discrete levels, and you would never think that you have a normal distribution just because of these discrete levels. But nevertheless, mathematically running a regression is possible as long as the assumptions of the normal distribution are not extremely violated. In this case, we are talking about pseudometric data. Let us sum up what we have learned about regression. So the first and most important message is, please do never just trust p-values without inspecting the model optically. Always take a very sharp look at the residual plot, whether there is some structure. The amount of variance, as we have seen, is not a problem for the model as long as the residuals remain normally distributed. Only the reliability of the prognosis decreases, means that the prognosis bands are getting larger if you have more variance. Eliminate outliers. This is one of the most important topics for a regression analysis. Eliminate your messy data. And then, last but not least, even on more problematic data sets, a regression analysis can be run. If you have questionnaire data not being metric, or data that is maybe not fully normally distributed. It is, however, very important that you document these flaws in your models with transparent reason, stating what kind of problematic assumptions you're making and reason why you use regression anyway, despite this assumptions may not be met. You can, for example, argue that you have very, very low p-values such that a slight disturbance in your assumptions may not affect the overall statements of your model. Since this can be a very advanced topic, we have a statistics consulting service at the Institute of Applied Simulation. I would especially advise you to seek our help in cases where you have nonlinear relations in your data, where you have heteroscedasticities or non-equal variances, or when you do multivariate regression. Multivariate regression will be the topic of the next podcast. We will try to give an overview of what you can do if you have more than just one variable x, but maybe you have x1, x2, x3, x4, and you would like to relate a target variable y to all these independent variables. The message for regression is also that you will not learn it unless you practice, so please use the scripts you find on Moodle in order to see and play with the different cases we have seen presented in this podcast.